Let's mathematically look at combinations. Now there's two different kinds of combinations. In combinations, remember the order does not matter. For example, we have two different types of combinations. We have combinations that do not allow repetition and combinations that allow repetition. Now an example of a combination that does not allow repetition is like a lottery number drawing. For example, if you have lottery numbers and the winning lottery numbers are 2, 14, 15, 27, 30, and 33, it doesn't matter what order those numbers are in. As long as you have that number in your set, you're a winner. So it doesn't really matter exactly which order those numbers come in. And the second flavor, as I just mentioned, it allows repetition, where you have, for example, you might go in your pocket and find out that you have a 5-cent piece, a 5-cent piece, a 5-cent piece, a 10-cent piece, and a 10-cent piece. Now, in this case, repetition is allowed, where we have the repetition of a specific coin. So we might have a 5-cent piece 3 times and a 10-cent piece 3 times. So we still have 3 5-cent pieces and 2 10-cent pieces. And again, it's a combination because it doesn't matter which order we would choose them. It still is 3 5-cent pieces and 2 10-cent pieces. And with lottery numbers, it doesn't matter which order, again, that we pick it. As long as we get a number from that list, we're good. And remember that the difference between the example for coins in your pocket and the lottery numbers is one has repetition is allowed and one does not. And again, for coins in your pocket, repetition is allowed because it's possible you can have, in this case, more than one 5-cent piece and more than one 10-cent piece. In the lottery numbers, repetition is not allowed. Think of a lottery drawing. Once that ball is chosen, you can't choose it again. So you don't have the capability of having that repetitive number. It's a simple concept, but sometimes it's really hard to kind of put your hands around that without going over some examples. I'm going to go over both those examples here. Let me start with combinations without repetition. And as I mentioned before, this is how lotteries work. If you have a number that's drawn one at a time, no matter what order you have those orders, you'll win. So the easiest way to explain it is, like for the lottery, is you might have 30 balls that are in that lottery, and then that little thing that shakes them up kind of goes off, and then you go and you pick a ball out, and that ball might be number 3. Well, when you go back in to pick a ball out again, 3 isn't there. So that number can't be repeated. So this is the example I'm going to go over here. Let's go over a pool ball example. In pool, if you play pool, you have 16 balls, as you may or may not know. And you have 16 balls that you play with. And let's say, for the sake of argument, that you're not including the cue ball. So if you wanted to figure out how many ways, or you wanted to know which 3 pool balls are chosen and not the order, there's a way to do that. So let's go over this problem again. Well, we want to figure out which 3 balls are chosen and not necessarily the order. Now, this is a little bit different than when you look at permutations, because if you look at permutations, you know that the order is important. So like for example, if you wanted to know the permutations of, picking 3 balls out of 16, you get 3,360. But remember, in this example, let's just say that balls 1, 2, and 3 are chosen. So here are the possibilities. If the order matters, it could be 1, 2, and 3, 1, 3, and 2, 2, 1, and 3, 2, 3, and 1, 3, 1, and 2, and 3, 2, and 1. That's the permutation. Remember, with the permutation, the order does matter. If the order doesn't matter, you just have one possibility. You have 1, 2, and 3. Remember, the order doesn't matter. So it doesn't matter if it's 2, 1, 3, 3, 2, 1, or anything. As long as there's a 1, a 2, and a 3 in there, it's a combination. So if you can take a look at this example, you can figure out and see that permutations always have, or in this case, in the demo that I gave you, has 6 times as possibilities as a combination. So permutations have 6 times as the possibilities as a combination. Now, there's an easy way to work out how many ways 1, 2, and 3 could be placed in order. And we talked about it in a permutation where you'd have 3 factorial. So to go over the example, 3 factorial would equal 3 times 2 times 1 equals 6. So you have 6 different ways 1, 2, and 3 can be arranged when the order does matter. And if we had 4 balls, we can try that where we have 4 factorial. So we have 4 times 3 times 2 times 1 equals 24. So that would be 24 different ways that we could have we could arrange the specific pool balls. But we have now is we got the problem where we have the combination here. Remember, in combination, order is going to be important. So we have our permutation formula. Now what we have to do is we have to reduce it by how many ways the objects could be in order. Because remember that we're not intended or even interested in the order they appear. So the formula would look like this. So let's talk about this formula in a little bit more detail. You might recognize the left portion of that formula is really the permutations. The left-hand side before the product where we have n factorial over n minus r factorial is a permutation. And then we multiply it by 1 over r factorial, which is the reduction, and that equals our combination. So see what I was saying before? You talk about combinations a little bit, and they seem easy, and they're not that hard, but you start to look at it in a little bit more depth, and it becomes a little bit more complicated. So what we can do is we can just take that equation and make something that looks like this. Basically taking the product on the left-hand side of the equals or the operator and make it look like the following, where we would have the permutation, which would be n factorial over r factorial n minus r factorial, and that would equal our combination. So this is going to take a little bit of trial and error. Just like any math problem, it's something that you need to try it to actually do it. I can only explain it to you, and I could go over an example of how it works in real life. And then I kind of expect you guys to take it from there, where you can, look at the example that I'm providing you, and then perhaps, stop the video and then go over it step by step, and certainly kind of go over examples that you can use. So basically, in our case, let's take the following. If we have 16 balls, 16 billiard balls or pool balls, and we want to choose 3 of them, basically it would be just like the lottery numbers. If we had 30 lottery numbers and 3 of them would be a winner or 4 of them would be a winner, we would have the following expression. We usually call this expression n choose r. N is the number of possibilities, and r is the number of choices we have. Now I'm going to let that soak in a little bit. N choose r. N is the number of possibilities. R is the number of choices that we have to make. Now in real life, that would be if we had 16 pool balls and we would choose 3 of them. How could they be arranged? Or in the lottery example, if I have 30 choices, right, and I get to choose 4, it would be 30 choose 4. So that's how we talk about this. So let's take a look at this formula again for the pool balls without order. And what I'm going to do here is I'm going to put in numbers in our equation and plug them in and go over this kind of a little bit step by step. And I realize that this is going over it a little bit too quickly. Like I said, with any math, you have to stop and you have to try it. One analogy I like to draw between math and music, it would be like if I was explaining to you how to play an A major scale, or if I was explaining to you how to play a C major scale, and you didn't know anything about major scales, and then I would just give you a 5-minute explanation and say, oh, okay, now you do it. You would say, I can't do it. I need to practice it. So that's where you're at with this. But let's go over the example. So if we have 16 pool balls and we choose 3 of them, first we could look at our 16 factorial over 3 factorial and choose r, which is 16 minus 3 factorial. So if we solve that equation, we still have 16 factorial over 3 factorial times 13 factorial. And you can just look at that and see where that math is coming from. Now, as I solve for this, I get a huge number, don't I? Take a look at this number here. It's like a gajillion. What is it? It's 20 trillion, right? 20 trillion, 922 billion, 989 million, 888,000 over 6 times 6 billion 227,000 20 I'm sorry 6 billion 227 million 20,800. That is a big number, but it's just a fraction. That's all it is. It's not any scarier than the fractions that you used when you're in second, third, and fourth grade, when you looked at a cookie and someone said if you took that cookie and you divided it by 4 people, how many pieces of the cookie would there be? Okay, well, you would have basically one cookie divided 4 ways. This is the same thing. It's just a big fraction. That's all it is. So as we solve that, we got the formula 16 factorial over 3 factorial times 13 factorial is the same as 16 factorial over 13 factorial times 3 factorial. Say that 10 times fast. So basically by choosing 3 balls out of the 16 or choosing 13 balls, they have the same number of combinations, which would be 560. So knowing that we have 16 factorial over 13 factorial, this again reduces to 16 times 15 times 14. So we can save a lot of the calculation. If we wanted to do it in a shorthand way, it would look like the following, and we would still get 560. Now, that's a lot. Now, let's kind of review what we did here. What we just did here is I just showed you an example of a combination without repetition. And what we did is we used the lottery for an example, and we used the pool balls for an example. So now what I'm going to show you is, since we're still on combinations here, is I'm going to show you a combination with repetition. Now remember, a combination with repetition means that if you have a number, you can choose that number again. Again, the example was those are the coins in your pocket. Like if you have 5 coins, it's very possible you can have 3 5-cent pieces and 2 10-cent pieces. I'm trying not to say nickel and dime because those are American expressions. All right, so let's take a look at the example here where I got combinations with repetition. Let's say we have 5 flavors of ice cream. Sounds good. I think I'll have some ice cream later. Let's say we have banana ice cream, chocolate ice cream, lemon ice cream, strawberry ice cream, and vanilla ice cream. So we have 5 different choices of ice cream. We're working at the ice cream store, and we have 5 different choices of ice cream. A person comes in and says, you know what, Mr. Ice Cream Man or ice cream lady, I want 3 scoops of ice cream. So how many different ways can I have 3 scoops of ice cream? That would be an example, kind of a fun example of combinations with repetition. Because I can choose 3 scoops of banana, right? I can choose 3 scoops of chocolate, 3 scoops of lemon, because we're not replacing it. It's not like if I choose a banana, I can't choose a banana again. I can. If I want 3 scoops of banana, I can do that. If I want 3 scoops of vanilla, I can do that. So this is important because we have combinations with repetition here. So basically what we'll do is we have, for example, for the equation, I'm just going to put in our set, I'm just going to say 3C. So C would equal, how about this? Let me give a letter for each of the flavors of ice cream. B for banana, C for chocolate, L for lemon, S for strawberry, and V for vanilla. So I can put together a matrix, like a one-dimensional matrix that looks like this. CCC stands for 3 scoops of chocolate. BLV, for example, can be 1 each of banana, lemon, and vanilla, and so on and so forth. I can have BVV, for example, 1 for banana and 2 for vanilla, and so on and so forth. So let be clear here that there's 5 things to choose from, and that's n. So n would equal 5, and we get to choose. Our choices are 3 of them. So we could say n equals 5, and R equals 3. Again, that's like saying choose 3 out of 5. So remember, order doesn't matter and they can repeat. So let's go over how we calculate this. Now, let's just look at this and let's think about the ice cream about being in boxes. I mean, we could say, like, move past the first box, then take 3 scoops. Then move along to 3 more boxes, like to the end, and we'll have 3 scoops of something, of chocolate in this case. So it's like we're ordering like a robot or a bot to get our ice cream, but it doesn't change how we want to get these. So we basically, what we do is we can write this down as the following, or we can put down our different choices with the arrow, and the arrow just means move and the circle means scoop. So we can have an algorithm that moves down the scoops of ice cream and gives us all the possible ways that this can happen. So in the 3 examples I had above, remember the examples? I had 3 scoops of chocolate. I had one each of banana. One of banana, lemon, and vanilla, and then 1 of banana and 2 of vanilla. I can look at it mathematically as this. I could say for the first one, move, scoop, 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 move, move, move. Just for example, there's more than this that are coming. I'm just trying to show you 3 of these. So basically our algorithm could be move, scoop, 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 move, move, move. In the second one, it would be scoop, move, move, scoop, move, move, scoop. And the third, right, when I want banana and 2 of vanilla, it could be scoop, move, 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 move. Say that 10 times fast. Scoop, scoop. So basically what we could do is we can mathematically look at this and build an algorithm on how we can pick 3 different choices out of 3 different decisions out of 5 different choices. Remember, we have 5 different kinds of ice cream and 3 different ways that we can choose from them. So anyway, so notice that there's always 3 circles here, right? Because that's what we're doing. We're choosing 3. And 4 arrows, because we need to move 4 times to get from the first to the 5th container. Again, think about these containers being right in front of us, and we're just kind of scooping as we go. So basically what we have here is we have R plus n minus 1 positions, and we want to choose R, and R are our different scoops of ice cream. So it's really equivalent of saying that we have R plus n minus 1 pool balls, and we want to choose R of them, but we're just using ice cream in this example. In other words, it's now like the pool balls in questions, but with a slightly changed numbers, we could write it something like this. So let's go back to the pool balls for let's not go back to the pool balls for a second, but let's look at the way that we can take our equation here, and we could just change the numbers a little bit to choose our ice cream example where repetition is important. So if you take a look at this equation, we have the following. We're going to have R plus n minus 1 factorial over R factorial n minus 1 factorial. Basically equals, and if you solve this, equals R plus n minus 1 over R. And n is the number of things to choose from, and we choose R of them. Remember, repetition is allowed, right? And order doesn't matter. So what will we get for our answer for that? So let's plug in our numbers here. So to solve this, again, how many ways can we have 3 scoops of ice cream from 5 choices would look like the following. It would be 3 plus 5 minus 1 factorial over 3 factorial 5 minus 1 factorial. We can solve that for 7 factorial over 3 factorial times 4 factorial, or, moving left to right, 5,040 over 6 times 24 equals 35. So the answer is there are 35 ways of having 3 scoops from 5 flavors of ice cream. Now, I think I need a break and have a little bit of ice cream, because to be honest with you, even though I do math for a living, if I just learned that, my head would be exploding, and I'd have to go back there, and I'd have to relook at this and kind of slow it down. But maybe you're smarter than me. If you're smarter than me, which is entirely possible, you got that the first time that I mentioned it, but I don't expect you to. I don't think math is very difficult. I think it's more about understanding simple concepts and then taking simple concepts and putting them all together for something complex. And then you look at it and go, wow, that was really hard. But it's not really. If you look at a math problem in very simple terms and kind of do it little bit at a time, you're going to find that it's very achievable. And that's what I want to kind of emphasize about just your mindset about doing math in general, where sometimes these numbers just bounce off the screen and they bounce through your head and you're just like, what is going on here? If you kind of go back and look at this, the most complicated math that we have is really boils down to four things, right? We can add things, we can subtract things, we can multiply things, and we can divide things. Now, you learned all of those skills in elementary school. Division coming to the last one. For some reason, division is a little bit harder to understand, but you start learning addition and subtraction, in kindergarten and first grade. And you start doing multiplication and division for me, it was like third grade we started doing that. So if you could do those four things, we call that arithmetic. If we can do those four things, any kind of math that we can do is possible, because all the math that we do, from making change at McDonald's to calculating the time dilation of a black hole, they're both math, and they're both based on addition, subtraction, multiplication, and division. It's kind of like a scale. If you play music, a scale's got 8 notes in it, but look what you could do with it. 8 notes could be chopsticks or it could be Beethoven, but it's still the same concept. Math works the same way. Learn the basics, take it in bite-sized chunks, digest it, and move on to harder things as you go. And that's what I tell people, just in conclusion here, about math. Or a lot of people say, well, I get this. I should be moving on to something else. This is elementary stuff. And I'm like, really? Is it really elementary stuff? It's almost like if you're a football player and you're making millions of dollars playing football, you probably, before you even play, you work out, you exercise, you run, you might do cardio. That football player that makes millions of dollars a year doesn't say, well, that stuff's beneath me, I don't need to do that. No, they do need to do that. As a mathematician, so do you. You need to go back and do basics, and don't think it's beneath you, because if you skip it, you're not going to be able to comprehend easily what comes later. Just like that basketball player that makes millions of dollars, that ice skater, or that football player that is at the top of their game. If they don't do the basics, they're not going to be able to do the hard stuff. You ask anyone that does things like that for a living, and they'll probably say the same thing, especially something that requires skill like boxing or ice skating. They'll say if you don't do the basics, you can't move on to the other things because you need to get the basics down. As a matter of fact, I was reading an article just the other day about the Chicago Bulls, a basketball team in my hometown in Chicago, and they had a really bad game, and the coach made them for the next practice do layup drills. And that's what they did. They did passing and layup drills, and not one person complained and said, oh, this is basic. We know more than this. Not one. They're just like, you know what? Let's get this down so the hard stuff becomes easy. Math works the same way. Start with things that you understand until it gets boring. You're like, oh my gosh, please, let's move on. Kind of like this lecture right now. And then move on to the harder stuff. So when you look at stuff like this, the combinations and the permutations, see how it's a simple concept, but when you write it out and you put the equations out and you look at them, you realize it's not as simple as you thought it was, but you have to work through it. You need to take your time. So the formulas I gave you here are kind of beginner formulas. I don't think that they're really that difficult, because they're certainly going to get more difficult as we go. But if you learn how to approach it, that's the most important thing. Learning how to approach a formula and how to solve a formula and how to solve an equation, learning how to do it is more important than the answer you get. And I know there's some math teachers, my brethren, that would roll their eyes at that. And they're like, Bob, the right answer is important. And I would say, yes, the right answer is important. But if you don't do the steps properly, you'll never get to the right answer. So you need to do the steps properly and methodically go through it and make sure it's correct, because if you don't do the steps, you can't get to the right answer. Believe it or not, I will say getting the right answer is the second step in solving an equation. The first step in solving an equation is developing a plan. What am I solving for? What am I doing? What are the steps I need to get there? What is my plan to solve this equation? Think about it. Dive right into that. Most of the most brilliant mathematicians in our day have done that. Einstein approached equations like that. Isaac Newton did equations like that. Anything that does trigonometry, if you're looking at trigonometry for for anything like space travel, or looking at angles, or looking at anything that has to do with any kind of algorithm, the first step is developing the plan. What am I doing? What am I solving for? What are the steps I need to do? Then you roll up your sleeves and you get in. But you can't roll up your sleeves and dive into it until you kind of get your hand around the problem. That's all I have for you. Thank you for listening, and I bid you all a very well rest of the day. Thank you.